Alright, hey guys, what's going on? So today we are going to be talking about probability distributions. We're getting back into the swing of things when talking about stochastics and statistical field theory. So with that being said, we're going to start now with talking about probability distributions. Make sure to hit that like and subscribe button. Now let's get straight into the content. So we're talking about probability distributions. It might feel like we're stepping back a few steps because we were talking about path integrals, and we were talking about Liouville's operations and all this kind of stuff, and Liouville's theorem. But I feel like I kind of have to do this. I feel like I kind of have to at least bring in some probability and some stochastic calculus because we're going to come across this later. This is sort of just an inevitable thing that we have to understand when it comes to talking about statistical field theory. And I kind of trying to rely on the minimum amount of prerequisites as possible. Again, I'm not in any boundaries or anything on how many topics or subtopics I bring up here. And so probability distributions, right? So we have to, so as we're going through this, we want to constantly keep on reminding ourselves of phase space. We've been talking about phase space. We've been talking about path integrals. We want to constantly keep on reminding ourselves of these things. And so we're going to constantly keep on tying things together as we go through this channel, or as we go through this playlist. So let's start thinking about probability distributions, right? So we were talking about them a little bit last time. We talked about how a point in phase space is a probability distribution, and those probability distributions change over time. Now let's put some tangible understanding to this. So consider a simple system, right? So this system is just a single penny, right? Now a penny can be in an upstate, which is the heads, or a downstate, which is the tails, okay? And so typically if your penny is a fair penny, it's not, one side of it is not heavier than the other. Our probability distribution looks like this. Looks like this right here. And really what this is we have the state axis, which is our x-axis, and our probability for each state, okay? And so for the head state, we have a 50% probability, and for the tail state, we have a 50% probability. Again, assuming this is a fair penny, okay? This is a very, very, very simple system. Let's talk about a system that might be a little bit more complex now. So this could be a one dice system, right? So a one dice system. So here's our system. It's a dice. It can consist of 6 states, right? Now there are dice out there that have like 8 sides or something like that, but we're talking about your common classical dice, okay? And this dice it has 6 states. Again, assuming it's a fair dice. No one side is heavier than the other or something like that. You don't have like a side made of lead or something like that. Then this is what our probability distribution looks like. Again, it's fairly simple, right? Because the idea is that 6 out of 6, well, that's 100% chance probability. 3 out of 6, well, that's 50% chance probability. 1 out of 6, and the reason we have out of 6 for all of these is because we have 6 states, okay? And so each state, again, has an equal probability of us having this right here, that we have a 1/6 chance of getting a 1, 1/6 chance of getting a 2, and so forth. Okay. The only difference between these two systems is that the domain of these states for the one dice system is larger right? Because we have more than one state that can come out of this system. Okay. Consequently, however, if the dice is fair, the probability of each state will decrease, right? Because here we had 0.5 on this spectrum lies right here. And so the more states you have, again, assuming all the states have an equal chance of, or an equal probability of occurring, this number is going to get lower. So we start from 0.5, we now go to 1/6, and if your dice has 10 faces, the probability becomes even less. So now let's think about a 2-coin system. or I have a 3-coin system here, but here we're actually, this is a 2-coin system, right? So that was a mistype. For this system, we have more states, right? So this is our 2-coin system. For our 2-coin system, okay, this is our system. We have 2 coins. Our probability distribution, well, there's still 4 possible outcomes here. So the only difference here is that, I shouldn't say still 4, right? Because up here we have only 2. Here we have 4 possible outcomes, right? So coin 1 is going to be heads, and then coin 2 will be heads, or coin 1 can be heads, coin 2 can be tails, coin 1 can be tails, coin 2 can be heads, or both could be tails. Right? So because there's 4 possible outcomes, this is what our probability distribution looks like. However, we run into this concept here called of degeneracy. Again, my apologies for the dog barking.
Hey guys, what's going on? If you're interested in this video and want to learn more about loop quantum gravity, string theory, and so forth, what you can do is you can become a member of this channel and you can gain access to all the videos that become uploaded on this topic and future topics as well. Again, thank you so much for your support and thank you so much for watching. This channel keeps on growing and growing, and I'm very excited to see where this is going to go in the future. So with that being said, make sure to hit that like and subscribe button if you like this kind of content. Make sure to become a member as well. Thank you, and bye.